up to this point, we've been talking about linear motion that has a constant velocity. But there's only a small subset of situations that applies for. A lot of times an object's velocity is changing. So in this video, we're going to talk about, well, how do we model mathematically a situation where an object is accelerating? And specifically, we're going to focus on situations where that acceleration is constant. And we're going to derive four equations that are super important that we're going to call the BIG4 equations. Okay, so in this video, we'll introduce those. So constant acceleration motion, what do we mean by that? Well, we mean that the velocity of the object is going to be changing at a steady rate. Okay, so if we look at our velocity versus time graph, anywhere on the velocity versus time graph where you have a straight line, there's going to be constant acceleration. Okay, so between 0 and 5 seconds here, we have constant positive acceleration. Up the top, we have acceleration equal to 0 because the velocity is not changing. So we have both constant acceleration and constant velocity, and the acceleration is just constantly 0. And over here, where we have a negative slope, we have a constant negative acceleration. It's still a straight line, so we know it's constant. Constant acceleration is very common. So objects falling from the sky, okay? They don't have a lot of drag. They're going to undergo constant acceleration. And a lot of times we model those objects as though they have constant acceleration. We have, okay, so that's the same example, kind of tennis ball. As soon as that tennis ball leaves that guy's hand, it's going to be undergoing constant acceleration. Okay, you slam on the brakes in your car. We can model that with constant acceleration. Or a skier sliding down the slope, constant acceleration situation. So these are very common. So this BIG4 set of equations we're going to be using quite a bit in the next couple units. So here they are, and we're going to spend the remainder of the video showing you where each of these equations comes from, what each of the variables stands for, and I will also give you an example problem where you can use that equation to solve a problem. Okay, let's take a look at our first of the BIG4 kinematic equations. For this equation, we are going to take a look at our definition of average acceleration, and we're going to make some changes to it. So average acceleration is your change in velocity divided by the time interval over which that change occurred. So let's kind of simplify things down here and call our average acceleration just AX. Okay, we're dealing with a constant acceleration. Our VF is going to change just to a VX, and then our T final is going to just be changed to T. I have a stupid fly buzzing around my head. I apologize. And then let's say that we're always going to say our initial time is 0, and we can keep V naught as V naught. So that simplifies our equation. It's the same equation, it just looks slightly simplified. Okay, and let's take this equation. So this is also telling us that A equals our change in velocity over time. But let's take this equation, multiply both sides by t, and we get an equation that tells us our change in velocity is acceleration times time, okay, for constant acceleration. And if we add our initial velocity to both sides, we come up with an equation for our velocity, Vx, as a function of time. Okay, we have basically an equation that tells us how the object's velocity is going to vary over time, what I just said. So let's see an example of when we might use this equation. In this example for equation 1 of these BIG4 kinematic equations, we're going to look at an airplane accelerating from rest on a runway at PDX, and it has an acceleration of 1.75 meters per second squared. And we know that this plane needs to be traveling at 65 meters per second in order to take off. And the question is, how long does it take the plane to reach its takeoff speed? Okay, I told you that we were going to be using this equation 1 where the velocity equals the initial velocity plus acceleration times time. But how would you know by reading this problem that this equation right here is a good one to use? Okay, well, you know the acceleration. You know the acceleration. You know the final velocity. So you know the final velocity. And you know that it accelerates from rest. So you know the initial velocity as well. So with this equation, you know everything except for time, and that's what you're looking for. So if you identify like what you know in the equation and identify what you're trying to find, that's how you want to kind of figure out what equation to use. So here we realize, okay, we know everything but one of the variables in this equation. So how do I approach this? Well, the first thing I do on any problem is I draw a picture. Okay, so here's my plane, and again we have a cool drawing of the plane. It's a dot. Okay, its initial velocity is equal to 0. And you'll notice I put, and I'm sorry, these kind of look like square roots, but this comes from like even when I was in high school. I add a little tail to my V's to like differentiate them from U's. So yeah, my V's, sometimes they're not square root signs. They're just, that's my V with a little tail to show velocity. And that also differentiates it from how I write volume. So volume I just write as an uppercase V. For some reason I put the little tail on the velocity. So those are what my V's look like. At some time later, we don't know, at some time t later, this is t equals 0, right? Remember, we're saying that initial time in this equation always equal to 0. So at some later time t, the plane or dot is going to have a velocity equal to 65.0 meters per second, and it will be able to take off because it's reached its takeoff speed. Okay, we know one other piece of information. We know the acceleration of the plane is 1.75 meters per second squared. Okay, we've set our positive direction to be to the right here in this reference frame. Okay, so there's our setup. I've identified my variables. Okay, now I want to figure out how I'm going to put this into the equation. So one trick in physics is you want to try to rearrange as much as possible your equation before you start plugging numbers in. Okay, so I'm going to try to start rearranging this for t. So I get an equation of t equal to something. So the first thing I can do, I can subtract v naught from both sides. Okay, and I get v minus v naught. Sorry. V minus v naught is equal to a times t. And then if I divide both sides by a, I give myself a nice little equation that t is going to equal v minus v naught divided by a. Okay, and once I have that, then I can plug my numbers in. So now let's plug my numbers in. I'm going to move over here. So we have t is equal to, well, my v is 65. My v naught was 0, divided by my acceleration is 1.75 meters per second squared. Okay, so this is in meters per second. This is in meters per second squared. So when we divide by a fraction, we multiply by its reciprocal. So if we're just looking at the units, this works out. We'll end up in seconds, which is what we want. So we take 65 divided by 1.75, and we get that the time that it takes for this plane to take off is 37.1 seconds. Okay, time for our second of our big four kinematic equations. So let's take a look. Remember, we have derived this equation for constant velocity motion, that our position is going to equal our initial position plus our velocity times our time. Okay, so that was that constant velocity equation. Here for constant acceleration, we know that our velocity, our average velocity, is going to equal our initial velocity plus our final velocity divided by 2. So if you're curious about that, we can go over that at a separate time. But in this video, I'm just going to tell you that because it's constant acceleration, we can say that this is true. So let's go ahead and take this and plug it in for Vx average. Okay, so we're taking this equation and plugging in for Vx average. We're now plugging in this V initial and V final. So V naught x and Vx divided by 2, and we're still multiplying by t here. Okay. And then let's take a look at our first equation, and we're actually going to substitute in for this Vx, V naught plus AT. Okay, so we make that substitution in there, do some algebra, and this is the equation we come up with. And this is actually a very useful equation. We use it a lot. This is probably the most commonly used of these 4 equations that I'm giving you. A very good exercise for you would be to try to do this derivation. So start with these three things and end up, through algebra, end up with this equation here. Okay, so I would encourage you to do that on your own. And you can come to office hours if you want. We can walk through how to do that. So this equation 2, tells us how the object's position varies with time if its velocity is changing, but it has a constant acceleration. Super useful equation. Let's check out an example of how we use it. So here's an example of a time when you would use this equation. So we have a situation where a biker passes a mailbox, and then he begins to accelerate at a constant 1.25 meters per second squared for 3 seconds. And during those 3 seconds, we are told that he travels 26.6 meters. So we'll say there's the mailbox that he passes, okay, and we'll call this x equals 0, okay. We know that at some time t equals 3 seconds after this time over here, x initial, right? So our x final is going to be 26.6 meters. So we've set our reference frame to be the positive direction to the right. This time equals 3.00 seconds. And that is what, oh, we also know that he started accelerating. The acceleration for this biker is equal to 1.25 meters per second squared, and it's positive, so we know it's in the same direction. Yeah, so we know it's in our positive direction in our reference frame. So now we need to rearrange this equation. So if we look at our equation, we know A, right? We know x, we know x naught, we know t. The only thing we don't know is our initial velocity. So we're going to want to rearrange this equation for v naught before we start plugging in numbers. Okay, it's an easy way to just avoid errors that are hard to correct. So the first thing let's do, let's subtract x naught from both sides. So it's minus x naught, so we got x naught equals v naught t plus 1/2 ht squared. Let's also subtract, so this whole term, we can subtract that whole term because we know a and we know t, okay, and we want to get v naught by itself. So let's subtract all that. Okay, so we got x naught minus 1/2 ht squared equals v naught divided by v naught times t. And then we're going to divide both sides by t. Okay, and now we have an equation that we can use that gives us what v naught equals. Okay, I'm going to be a little lazy here, and I'm going to not rewrite that over there. So, okay, so now we have our equation that we can directly plug and chug into. So my v naught is going to be equal to, well, my x is 26.6. Okay, my x naught is 0. Okay, so we don't even really need to write that, do we? And then minus 1/2 times a, which is 1.25, times t squared, which is 3 squared. And then we're going to divide by 3. And that's going to equal 6.99. And our units, we're looking at a velocity, so meters per second. And let's check our sig figs. So we have 3 sig figs and 3 sig figs and 3 sig figs, so we can report 6.99 meters per second. So that was the velocity of our biker as he passed that mailbox. Okay, our third of the kinematic equations, we are going to start with that first equation we found from our definition of acceleration, and we are going to rearrange it so we're solving for t. Okay, so I subtract v naught from both sides and divide by a, and I get this relationship here that time can be found by our change in velocity divided by the acceleration. Okay, we're going to use that, and we are going to plug that into our BIG4 equation number 2 that we just derived and looked at. So we're going to substitute in the vx minus v naught x divided by a for both of those t's in there. Okay, and do some algebra. And then we can come up with this equation. That, again, great exercise for you would be to go through and see if you can do the algebra to start with these two equations and end up with this one. Okay, looking at each of these variables and what this equation means, or what this equation is used for. Equation 3 expresses the object's velocity when the object is at a given x coordinate, and the key with this one is that there's no reference to time. Okay, let's take a look at an example using this equation.
Looking at another example here. So now we're going to use this third equation of the big four equations. We have a ski jumper traveling down a straight section of the in-run. So they're like in the part before the jump. So a straight section here. Okay. If she enters the 42-meter straight section traveling at 39.5 kilometers per hour, and experiences a constant acceleration of 5.2 meters per second down the slope, what is her velocity as she leaves that section? Okay, so here's our skier. Again, a really cool dot that we can model that skier as. And she's entering this with a velocity, and this is a 1D, one-dimensional problem. So what we can do is, let's just go ahead and, so the skier has a velocity, initial velocity of 39.5 kilometers per hour. Okay, make note of the units here. That's not in meters per second, so we're going to have to come back and probably do something with that. So let's notify ourselves here that we have units that are not meters per second. And this straight section is 42 meters, so we can call this initial position 0 meters and this final position equal to 42 meters. Okay, and we know that she has a constant acceleration down the hill of 5.2 meters per second squared. And that is all we know, folks. So this is one where we have no time information. So if you have no time information, this equation here, this third equation that we're going over, is a useful one to use. Okay, so we do know initial velocity, we know acceleration, and we know the displacement. Okay, so what we're trying to find is what is her velocity when she leaves that section of the in-run. So we are trying to find velocity here. Okay, in order to plug these numbers in, so far I had been nice in these other examples that I gave you, and we didn't have to do any unit conversions. Everything was in meters or seconds or meters per second or meters per second squared. Here we have a kilometers per hour. Okay, so I'm going to go ahead and scroll down a little bit now that we have the picture drawn, and we need to convert this 39.5 kilometers every 1 hour into meters per second. Okay. You need to be consistent with your units, or these equations are not going to work. I'm going to keep more decimal places than I probably really need, but I don't want any rounding error. Okay, so that's my new initial velocity that I'm going to want to use. Okay, so there is my initial velocity. Okay, now that we got this taken care of up here, now let's go ahead and rearrange this equation to get us what we want. Well, you can do this one of two ways. You could just plug it in right away and then take the square root of your answer, but I like to rewrite it so I don't forget to take the square root at the end, because that's kind of a common thing, to forget to take the square root. X minus x naught. Okay, so there's my equation that I can just kind of plug and chug now. I know my initial velocity. I just found it in the units that I want. So my velocity, square root of initial velocity, 10.972 squared plus 2 times my acceleration. Now I look at my signs whenever I'm looking at my velocity and my acceleration. If they're in the same direction, they can both be the same sign. So my initial velocity was positive, so I can make my acceleration positive as well. They're in the same direction. 5.2 times x minus x naught. Well, x is 42, x naught is 0. Okay, so we plug that into our calculator and we get 23.6 meters per second as our velocity of that skier when they leave that section. And that is equivalent to like about 85 kilometers per hour. Okay, so you could report either. You would need to round to 2 significant digits, because if we look back at the numbers we were given 42, 5.2, both have 2 sig figs. So you could report 24 meters per second, or if you wanted to report the 85 kilometers per hour, you could do that too.
Equation 4, this one's a little bit different with how we're going to derive it. We're going to take a look at a velocity versus time graph and think about what it means. So we talked about last time, or last series of videos, that if you find the area underneath a v versus t graph, that's going to equal the displacement of the object over the time interval that you find the area. So here, if we wanted to find the area, we can split this into a rectangle and a triangle here. Okay, so the rectangle and the triangle there. If we were to find the area, we would add the area of this rectangle to the area of this triangle. Okay, so let's look at what that looks like. So the displacement is going to equal the area. Well, the area is v naught t, so that's the area of this blue rectangle. Okay, plus 1/2 the height times the base of this triangle here. So we get our height by taking v minus v naught. Okay, and our base of this triangle is t. Okay, so that's our area of the triangle. This is our area of the rectangle. We add them together and we get the displacement. Okay, we talked about that last time, that the displacement is equal to the area under the velocity versus time graph. Okay, so with a little rearranging, and not a lot of rearranging, but again, see if you can do this for yourself. You're gonna, rainbow method in, or whatever you call it, distribute the t in, do a little algebra, and you can come up with the displacement equaling 1/2 times the sum of the two velocities, the final and initial velocities, times t. God, I have a fly just buzzing around. I'm so sorry. Okay, well, let's take a look at when this equation is useful. Oh, I didn't mention it. Equation 4, this one expresses the displacement over a certain time period given the change in velocity. Okay, so you don't see any a in this equation. There's no acceleration present. So if you don't know the a, this might be a useful equation to use.
Looking at our example problem for this fourth equation, we have a bus driver who sees a wounded dog on the road ahead. At that point, the bus is traveling at 23.5 meters per second. So here's our bus. And it's traveling at 23.5, our initial velocity, 23.5 meters per second. The bus driver applies the brakes and brings the bus to a safe stop. So we know it time equals 12.1 seconds. The velocity of this bus is now 0 meters per second. And our time over here, our t is 0 seconds over here. So the question is, if the bus slowed at a constant rate, how far from the dog was the bus when the driver first saw it? We are trying to find basically the displacement. So here's the initial x position, here's the final x position. So we want to find how far away these two positions are. So we're finding the displacement here. Okay, between where the dog was, okay, and where the bus was when the driver initially saw it. So the key to this, when you want to know how to use this equation, is that you don't have any acceleration. So the problem doesn't give any acceleration value. It does say the bus slowed at a constant rate. So we know that it's constant acceleration, but we don't know what that value is. We do, however, have information about the initial velocity here, the initial velocity, the final velocity, which is 0, and the amount of time it took, so 12.1 seconds. Okay, so this equation actually is already set up for us to solve for displacement. So all we need to do is plug in our numbers. Okay, so let me change colors here. We got our
displacement, which is what we're trying to solve for, is equal to 1/2 times v plus v naught. Well, our v is 0, and our v naught was 23.5. That's 23.5. And then our time is 12.1 seconds. Okay?
We plug that into our calculator and we get that the displacement is 142 meters. We check our sig figs. Well, we have 3 significant digits, 3 significant digits. So I'm going to report my answer in 3 significant digits.
So there you have it. We went through these 4 equations. We will be using these a lot in the coming weeks. Thanks for watching. I hope this was helpful.